Today's lesson is on dimension change for similar solids or similar figures. We already did dimension change last unit in 2D figures. It was the 1D to 2D and the 2D to 1D. The A is to B as A squared is to B squared. It was that step. Well, now we're going to do it with all three dimensions, which is as far as we're going to go. So first, we're going to do the slide where we discover what the dimension change is all about, and then we'll practice problems with it. Okay, so first let's just write down some data. The width or the height, it doesn't really matter what we put here. We'll call this the width, even though you might call it the length. Doesn't matter to me as long as we picked one of the sides. Okay, let's find the surface area of both of these prisms. Go ahead and find their surface areas. Good. All right, the surface area of the smaller one is 32. The surface area of the larger prism is 288. Okay, now let's do volume. This one's way easier. Length times width times height. 3 times 2 times 2. What is the volume? Hate them? We're not doing that yet. What is the volume? 3 times 2 times 2. 12 for this one. 6 times 9 times 6. 324. All right. So these are real prisms, and those are their real areas and their real widths and their real volumes. We don't care about their areas and their volumes, but what we do care about is the ratio of their areas and their volumes today. Remember, this only works, what we're going to learn today only works on similar solids. All right, so the ratio of the width to the width is 3 to 9, which reduces to 1 to 3. Go to your calculator and reduce. 32 to 288, math, enter, enter. That reduces to 1 to 9. And the volume, crazy, huh? 12 to 324, math, enter, enter. What this is saying is that if you take a solid, we'll call it a prism this time, but it doesn't have to be a prism, and you triple its dimensions, you're only tripling its dimensions. Its dimensions get 3 times bigger. But what are you doing to the volume when you triple the dimensions? It sounds so innocent, like, okay, triple its dimensions. Scale factor is 3. Scale factor is 3. But you make the volume literally 27 times bigger. 27. And where these come from, you're already saying it. Where these come from is the scale factor is 3. So the ratio of the sides is 3 to the 1. The ratio of their areas is 3 to the 2. And the ratio of their volumes is 3 cubed, 3 to the 3. Because sides and perimeters are 1D, area, even surface area, is 2D, and volume is 3D. Cool, huh? So the dimension, oh, that's sweet, Hayden. The dimension matches the exponent. If it's 1D, the exponent is 1. If it's 2D, the exponent is 2. And if it's 3D, the exponent is 3. Now, what are you raising to this exponent? You're raising the scale factor to whatever exponent you need. All right. Easy enough. Let's write that down in our notes. Let's summarize that in our notes. If the similarity ratio of two similar figures is A to B, then the ratio of their perimeters is A to B. The ratio of their areas is A squared to B squared, and the ratio of their volumes is A cubed to B cubed. Just like last lesson, except now it's A to B, A squared to B squared, A cubed to B cubed. Remember, this is a ratio, so we'll be reducing our answers. We're not finding the volume, we're finding the ratio of the volume. Just to let you know, other words I could put here, it's the ratio of their perimeters, it's the ratio of their heights, it's the ratio of their lengths. Anything that's a segment I could put here. Ratio of the sides, ratio of the slant height. I could put any of those words in the A to B part because all of those are segments. They're all one-dimensional. So the ratio of anything that's one-dimensional is A to B. Surface area, I don't care if it's total or lateral. Either one belongs in this category. If it's an area of any kind, its ratio is a squared to b squared. In volume, there's no other way to put volume. Volume is volume, a cubed to b cubed. Let's try it. Aren't those cute little water bottles? Find the ratio of area and volume for the similar water bottles. So that's important. You have to know, you have to be told that they're similar. So these are the same water bottle even though their lid is different. They're just different sizes. One is for a little kid, I guess, and one's for a big camping trip or something. All right, so you were given diameters. Given diameter of the base. I want to know the ratio of the heights. So here's the reminder. You cannot find the height. You will not find the height. You cannot find the height. But you can find the ratio of the heights, because if the ratio of the diameters is 3 to 4, diameters are 1D and heights are 1D. So the ratio of their heights is 3 to 4. What's the ratio of their surface areas? Cool. Square the 3, square the 4. Good. And finally, the ratio of their volumes. Make sure you know how to cube something in your calculator. 3 cubed is 27, and 4 cubed is 64. Easy enough. There's no tricks here. That's it. Let's try some more. The ratio of the volumes of two pyramids is 125 to 512. What is the ratio of their size? It did need to say two similar pyramids, so let's put that word in there because that's actually of utmost importance. But you know what we don't care about? We don't care that they're pyramids. Don't go to your formula chart and find the volume of a pyramid. That's the beauty of this, is that if they're similar, we actually don't care what shape it is. We only care what dimension we're in. Okay, so if the ratio of their volumes, I know y'all already know the answer. This is 3D because it is a volume. We want it to be 1D because sides are one-dimensional. So how do you undo 3D? You cube root them to make them 1D. Math 4. Math 4. The cube root of 125 is 5, and the cube root of 512 is 8. Love how y'all were fighting about who got it first. 5 to 8 is the answer. Ratio of the sides. The edges of a large cube are 4 times longer than the edges of a small cube. How many times greater is the volume of the large cube? Sometimes it trips people up when you put it in a word problem, but you don't treat this one any different than what we've been doing. Go ahead. You can type the answer if you want. Edges. I'm gonna circle the keywords. That's all you need. Cubes are all similar to each other, by the way. We don't even need to say they're similar. Cubes are all similar. You only need 3 items from all of those words. You need to know that 4 represents edges, making 4 one-dimensional. You need to know that they're asking for the scale factor of the volume. And so we need to convert this to 3-dimensional. You know the drill. We've already cubed 4 today. 4 cubed is 64. I cannot tell you guys how many people are going to pick 16. They're going to do 4 times 4. Or how many people are going to pick B, 4 times 3, because 3D, they're going to do 4 times 3. People still pick the wrong answer, I promise. Oh, that's great. Yu bought a rectangular box to display her doll collection. Isn't it pretty? A good collection. She decided to exchange the box for a similar one that doubled the dimensions because she has more dolls. How does the volume of the larger rectangular box compare to the volume of the smaller ones? All right, so we know that we have similar vases. That's good. Their areas, so it's 2D. Their areas are 36 and 100. Oops, I was about to put it up. We know that 36 and 100 are 2D values. The larger vase has a height of 15, so if we're going to write a proportion, we need to put 15 where the larger one was. But we know that height is one-dimensional. So this side of our proportion is one-dimensional. What is the height of the smaller one? So just be careful. The only way you could mess this up is you could cross-multiply a 2D with a 1D. Bad, won't work. Math doesn't work that way. So we want to convert everybody to 1D because that's where X is. So the way to undo 2D is to square root. So it's not 36 is to 100, it's 6 is to 10 as X is to 15. Make sure you check. These are 1D, these are 1D. Okay, you're allowed to cross multiply. And the height of that smaller vase was 9 inches. Yep. Ooh, how pretty is that? It's a cylindrical aquarium in Berlin. Isn't that so pretty? Okay, so that's a very large fish tank. It has a volume of 800 cubic meters. Think of a meter stick. And then 800 cubic of those. Okay, anyways, so someone's going to produce a similar one. They want to copy this one, but ooh, they do not have the budget for this one. So their fish tank is going to have a scale factor of 4/9. That means 4 is smaller than 9, so you're making it smaller. It's going to be 4/9 the size. Find the volume of the new tank. So I'm going to teach you 2 ways to do this. I'm going to teach you 2 ways. One way would be 800 times my scale factor. But before I multiply, I'm going to make sure volume is 3D. Uh-oh. Scale factor. Scale factor is just the factor of the dimensions. It's always 1D. So I cannot multiply these. I need to convert everybody to 3D because I need to find the volume. So I could do that. So I could do 800 times my scale factor cubed. Or I could go the proportion route. Kind of. It's not really going to work as good. 800 is to what? Well, that's my question mark. As, it would actually have to be 9 is to 4. You need to put the big one with the big one and the small one with the small one. This is 1D, sorry, this is 3D, this is 1D, so you would cube it and cross multiply. That's going to get the exact same result. I think using the scale factor with the fraction works better, but if you want to set up a proportion and cross multiply, you're going to get the same thing. Okay, so did you find it? Yeah, it's a real world problem. They don't always work out nicely. So 800 times 4/9 cubed. 70. Yeah, math enter. So exact answers are fabulous and I love them, but they don't have much clout in the real world. They don't make much sense in the real world. So the volume of the new tank is about, this means about 70.2 cubic meters, not centimeters, sorry, cubic meters. So it's smaller than 800. It's quite a bit smaller than 800. They might be able to afford that one. All right, we've already done one like this, so I'm going to skip the Twix problem. This is our last one, last problem. Okay. 2 similar cones have volumes of 216 and 512. If the radius of the smaller cone is 9, what's the radius of the larger cone? This is a good old proportion one. 216 is to 512. Stop right there. Those are volumes, so put a little dimension bubble above it. I call it a dimension bubble, like so you can keep track of what dimension you're in. The radius of the smaller one. So the smaller one would go on top so that it matches. And it's a radius. Radius is a segment. Radius is 1D. So right now we can't cross multiply. I don't want to cube 9. This time I'm not going to cube 9 because I need my answer to be one-dimensional. So I need to undo This 3D, you need to go to 1D. The way I undo it is cube root. Cube root of 216. 6, cube root of 512, 8. So you can write a new one. You don't have to reduce it. And now you can cross multiply because this is 1D and 1D. 9 times 8, enter, divided by 6. The radius of the larger cone is 12 centimeters.